Ladies and gentlemen, good morning. I would like to acknowledge my co-authors. Just to touch on the background, accurate estimation of relationships between animals is an important step in any routine genetic evaluations. Relationships were previously based on pedigree information only. Conversely, most current evaluation use both marker-derived matrices and pedigree-based relationships. Genomic estimators are more accurate than pedigree-based because they have more variation between closely related animals, and this is more clear for half SIPs and full SIPs. The accuracy of genomic estimators may be even higher if founder population allele frequencies were available, but in their absence, current population allele frequencies are used to make G, and that defines the founder population. The use of observed allele frequencies in structured populations, however, may lead to biased estimation of G. And therefore, the objectives of the current study were to estimate pedigree and genomic matrices. And for genomic matrices, we use different methods using either observed allele frequencies across breeds or breed allele means. And furthermore, we estimated breeding values and direct genomic values using different G matrices. And later, estimated coefficients and their respective genomic values were compared. The study was carried out in the Nordic red dairy cattle, which is a combined population with three subpopulations from Denmark, Sweden, and Finland. It is the second largest breeding population with effective population size larger than that of the Holsteins. And most animals in the data, about 98%, are composite of breeds. Here, the absence of purebred animals remains a major limiting factor for the estimation of breed-specific allele frequencies. We used genotypes of about 40,000 SNP markers for over 4,000 bulls. We calculated breed proportion for bulls from the full Nordic RDC pedigree, which had more than 4 million animals. From the breed proportion data, 3 main breeds were defined with mean breed proportion over 10%, and these were the Swedish Reds, the Finnish Ayrshires, and the Norwegian Reds. The remaining breeds with mean breed proportion less than 10% were put together into breed other. Phenotypes were cow individual daughter deviations for milk, protein, and fat from 2010 Nordic genetic evaluations. Genomic relationships were estimated essentially following methods that were described by Van Raden, method 1 and 2. And here, G estimated using observed allele frequencies, we called it GOF, and it was defined by ZZ prime divided by K, where an element in Z was 0, 1, 2, number of the second allele, as deviations from the 2PJ, where PJ is the frequency of the second allele. And the expression K was the variance of the marker. And here, the matrices that were estimated using breed allele means, we call them GBM and GBM2 for method 1 and 2. And the first one was defined by MM prime divided by K, similar to Z. However, this side, PIJ, is the expected allele frequency of marker J for bull I, given its base breed proportion. And PIJ was computed by a simple multiple regression of genotypes on breed proportions. Modifying method 2 from Van Raden, in his matrix, it was defined by the ZD prime divided by M, where a marker is scaled by its variance, which is equivalent to standardizing the genotypes, and M is the number of markers. Similarly here, we defined our matrix as MM prime divided by M, where our markers instead were standardized by the expected breed allele means and their standard deviation. Alternatively, we considered matrices that combine both genomic and pedigree information, and pedigree relationships were estimated for genotype bulls only using RELAX2 computer program. G with observed frequencies and G with breed means were combined with 20% weight on the pedigree to yield GNA with observed frequencies and GNA with breed means. And this is the formula that we considered to do the weighting. Variance components, breeding values and genomic values were estimated separately for each matrix using GBLUB. Here we used AES-REML and Mix99. And this is the module that we used, where in Y we had a cow individual data deviation, and then B is the vector of fixed mean and breed regression effects, and A is the vector of breeding values or genomic values. The breed regression effects were used only for predictions that used breed means, and predicted values included fixed regression solutions. Here I should also mention that our analysis were weighted by the effective data contribution of the cow. There's a lot of numbers here, but if we look at there are 4 blocks, we looked at the coefficients when the populations were combined and separately for the 3 subpopulations. And if you look at the mean and the maximum values, when you look at A, the range for A is generally smaller than the range for the genomic estimators, which is very much expected. And when you look at the mean for all estimators across populations, they are close to 0, and also in the Swedish population and in the Finnish population. However, if you look in the Danish population, when you use observed allele frequency, the mean for the diagonal elements as deviations from 1 is 0.136. And also, when you look in the Danish population, A is, when you use pedigree relationships, or when you consider pedigree relationships, the Danish bulls had the lowest diagonal elements, mean diagonal elements, and the Finnish bulls had the highest mean diagonal elements. However, when you consider genomic estimators, this has been reversed. You find that now the Danish bulls have the highest mean diagonals, and the Finnish bulls have the lowest mean diagonals. We also considered the histograms for also the diagonals as deviations from 1 for all the estimators. And here we categorized the elements from those that had diagonals less than 0 to those that had diagonals over 0.6. And when you consider A, the bars are about the same, both when the populations are combined in the Swedish, the Danish, and the Finnish population. When you look at the G with observed frequencies, there seem to be some, across populations, there seem to be some animals with mean diagonals, with diagonal elements that fall in the category 0.1 and 0.2 and over 0.6. And this is more pronounced now in the top right figure, with the Danish bulls having, half of the bulls having diagonals that fall between 0.1 and 0.2, and about one quarter of them falling over 0.6. The bars for the G with breed means were about the same in all the populations. However, there seem to be many animals that shifted into the category where there were diagonals less than 0. And this is even more pronounced by G using breed means and method 2. Here we considered the correlations between A and genomic matrices for pairwise relationship. When you look at the correlation between A and G with observed frequencies, we find that the correlation is 70%, and then when you use G and with breed means, the correlation was 0.66. If you go down to within the Danish population, the correlation between A and GOF is now 0.64, and then the correlation between A and G with breed means is 0.86. The correlations between the between A and genomic estimator and between the genomic estimators were about similar for the Swedish and the Finnish bulls. And now we also looked at the correlations between the estimated breeding values and genomic values from different estimators for validation pool. And here A, EBV is for, the parent average. The correlations between the correlations for animal solutions between genomic estimators were 1, indicating that solutions were all the same from from each of the matrices. And this is also the same for genomic estimators that combined both genomic matrices that combined genomic and pedigree information. The first line the correlations between our matrices and pedigree, they were 0.67 or 67% for matrices that only use genomic information, but the correlation increased by 10% when you combine pedigree and genomic information. In conclusion, the use of simple observed allele frequencies across breed overestimate values in G for populations with least number of animals in the combined data, and or individuals from distantly related populations. Estimated breed allele means reduced country coefficients, country differences in coefficients similarly, but it shifted them too much towards 0 or less. The prediction of genomic values converged to similar solution regardless of allele frequencies used. And here, inclusion of breed regressions for G with breed means brought breed means back into the predictions. The validation accuracy, I didn't show any validation reliabilities, but this is coming out also from the correlations that they increased slightly when pedigree and genomic information were combined, hinting us that a single step from G with breed means and pedigree, including non-genotyped animals, could increase the prediction of DGV even more. Thank you very much, ladies and gentlemen. If there are any questions, I'll be happy to answer.